Hi, I'm Terry from Delta Tech, a member of the TANGO Project. In this video, I'm going to explain and demonstrate the advantages and benefits of the key component of the Tango toolbox, the AMPS programming model. First of all, I will detail a bit what is the programming model and its possibilities. Afterwards, I will illustrate the simplicity and the powerfulness of the programming model through a typical use case of an embedded application. During this use case, we will measure the execution time of the application to illustrate the efficiency of the programming model. AMPS essentially enables the programmer to create tasks that will be executed asynchronously and by this way enabling very simple parallelism. To create a task, the programmer only needs to precede the code of its task by a compiler directive in a similar fashion as with the OpenMP API. AMPS manages data dependencies very efficiently so that the programmer only needs to inform the programming model what the inputs and outputs of the tasks are. The application must then be compiled with the Mercurium compiler and will be executed through Nanox runtime system. This runtime will then help the execution of the application, managing the launching, execution and synchronization of the tasks that have been created, ensuring the proper scheduling of these tasks to take dependencies into account. This whole architecture allows something that is unique and very interesting for modern platforms. It supports heterogeneity. Not only the very exact same code can be compiled for different architectures such as Intel x86 or ARM without any change by the programmer, but most of all, the programmer can ask for a given task to be executed on a distinct compute unit such as a GPU thanks to OpenCL kernels or even on an FPGA. The compiler will generate all boilerplate code needed to transfer the data from one unit to the other and to fire up the execution. It will then be the responsibility of the runtime to dispatch and execute the program on the available compute units. This is illustrated in our test use case, in which we build our application for two distinct platforms, an IMX6 platform and a Zinc platform. This video only highlights the IMX6 platform on which OpenCL kernels will be executed through AMPS. Let me first detail a bit the scenario of the use case. This is based on a typical embedded application of Delta Tech. The aim of this project was to validate water meters indications using image processing. The value read with the image processing algorithms was then confronted to a reference value. As you see, the water meter is accompanied by a barcode that identifies the meter. The sequence of the algorithm is depicted on this picture. As in many image processing algorithms, the steps are to be executed sequentially. That is, that a step must be fully completed before the next one can be run. The algorithm is written in C. In the Tango project, the objective is to implement the algorithm on an IMX6 platform. This is a typical microprocessor for the embedded application, hosting 4 cores, ARM processor core running at 1 GHz, and a Vivante GPU able to run OpenCL kernels. This processor is on an evaluation board, providing a gigabit Ethernet interface, a USB port for connecting external devices, and a USB port providing a serial connection to connect a remote console. The evaluation board is currently powered through a watt meter that can be controlled by USB directly from the embedded processor to measure the energy consumed by the board. Okay, let's now see the systems running. The development environment is mainly running on Windows system hosting virtual machines and Visual Studio. There is one virtual machine for targeted platform, the IMX6 and the Zinc platform. As you see, virtual machines are running a standard Ubuntu 64-bit system. Inside the virtual machines, you will find all components needed to cross-compiling this Ubuntu virtual system targeting the embedded platform. Especially on the top left corner, you see the compilers running on 64-bit systems targeting an ARM processor. We are mainly interested in GCC and G++ compilers since our application is written in C. You see on the bottom left the so-called sysroot. A sysroot is a special folder on a system that replicates the hierarchy of another system with all needed file systems such as libraries. For instance, the library needed by the OpenCL runtime, and you see here that this library is an ARM library. On the right hand side, you see the ARMS environment deployed on the Ubuntu system. Especially, you have folders for Mercurium and Nanox. Inside Nanox folders, you find the standard compilated structure of Nanox with binaries and libraries, especially performance libraries that are of interest in here, since these are the files that are deployed on the target platform, the IMX6. Let's have a look at the development environment inside Visual Studio. As you see, I left one of my files opened. This actually is the file hosting the OpenCL code. Anyway, let me open one interesting file, processing. This is where you'll find the heart of the algorithm. You see the different steps of the algorithm: ajustement de fromage, ajustement éclairage, sorry for French names. ARMS instructions are inserted in this file. Let's see. The start of an asynchronous task, a parallelized for loop, and so on. To build this application, we use a plugin to Visual Studio that is called Visual GDB. The main advantage of such a setup is that I have only one solution and one source code for all targeted platforms. To choose the one I'm working on, I set up different configurations. You see here several configurations for both IMX6 and Zinc platforms, a standard one to use ARMS, one with OpenCL and ARMS together, and so on. To compile, Visual GDB constitutes a standard makefile that can be edited, then sends the source files on the virtual machines, and executes the cross compilers through an SSH connection. Here I'm linked to the OpenCL library that is in the sysroot folder I've shown you before, and activate the ARMS compilation for Mercurium. Okay, let's get back to the main window and do a standard 32-bit CPU compilation. This is our initial situations that we aim to enhance. You see that Visual is using the ARM cross compilers to compile our source files, all our source files. Okay, the compilation succeeded. Now, Visual GDB is configured to directly send the built executable files and needed dependencies to the targeted platform. So I'm already ready to run. Let's get to the console of our IMX6 platform and run our application. For efficiency purposes, the program does not print anything while working. To get a more accurate timing measurement, the program will decode 100 times the same picture. Let me also open the input picture of the algorithm. This is the water meter the algorithm just read. If we add the dial with our eyes, we read the value of 7,918. The last digit is somehow halfway between 8 and 9. The program returns the value of 7,918.52. This is a fixed decimal representation. The barcode is properly read as well, 864. Perfect. Let's close this. We are going to build a ARMS version of the program. As you see, the program now calls Mercurium compilers before calling our ARM cross compiler. Okay, let's run this. The return value are correct. It's very faster, as you see. Our standard compilation needed more than 18 seconds to execute. This version only needs a bit more than 5 seconds. Very conclusive. Okay, let's do our final build, a OMS OpenCL compilation. Oh, fast build. Okay, let's run this. You see I already have OpenCL initialization messages, so perfect. Yeah, the return value is still correct, but the time to run has increased. We now need almost 15 seconds. You also see the Nanox information about the transfer between CPU and GPU. This concludes our presentation. I hope you enjoyed it. For further information, don't hesitate to visit the website of the Tango Project, tango-project.eu. Thanks for watching.